Hello and welcome to Common Core Algebra 2 by eMathInstruction. My name is Kirk Weiler, and today we're going to be doing a video for one of our add-on lessons, Unit number 4, Lesson number 7.5, which basically just means it's supposed to lie somewhere between Lesson 7 and Lesson 8. Today we're going to be looking at exponential modeling revisited. We felt like we needed to add another lesson on exponential modeling that looked at exponential modeling where maybe you have to transition between certain time units in our modeling. Let's jump right into this in terms of a problem that you've seen many times before, and that's where we're looking at how long it takes for a population to double. Let's jump right into that. All right, here we go. Let's take a look at exercise number 1. I'll read it for you. Exercise number 1. A colony of fruit flies has a population that doubles every 8 hours. There were originally 22 fruit flies in the population. Now, I always encourage kids before they jump into a problem and start working through it that they really understand what's going on here, right? So at 0 hours, right, we're sitting with 22 fruit flies. After 8 hours, we get to double once, and we're now at 44 fruit flies. After another 8 hours, so a total of 16 hours, we're now at 88 fruit flies. And we'll continue that doubling every 8 hours. Let's take a look at what the first part of this exercise asks us to do. Letter A. If P represents the population of fruit flies and D represents the number of times the population has doubled, write a model for P as a function of D. Now this is very important, right? What I want is simply an exponential model that predicts the population of fruit flies as a function of the number of times it's doubled. So right now, I'm not bringing in the fact at all that it doubles every 8 hours. And this is pretty easy, right? So generally speaking, most simple exponential models we try to model in the form of y equals a times b to the x, with no little dot down there, all right? What we're going to be doing this time, though, is our output's not called y, it's called p for population. Now remember, the a is always our initial amount, which in this case is 22 fruit flies. And our multiplying factor is 2 because we're doubling, right? Our variable now is simply how many times we've doubled, okay? And of course, you can test this quite easily on your own. Right? If we let d equals 1, which means 1 double, well then we would have 22 times 2 to the first, or 44. On the other hand, if d was equal to 2 doubles, or 2 doubling, if you will, then we would have 22 times 2 squared. 2 squared is 4, 4 times 22 is 88, etc. All right, now remember, this doesn't take into account whatsoever the amount of time it takes to double, and that's what we really want to get into. So let's take a look at letter B. All right, letter B says, if h represents the number of hours since the population was originally at 22, what is an equation that relates h to d? Solve this equation for d in terms of h. Now again, nothing to do with population, okay? We just want to relate the number of hours that have passed to the number of times it's doubled. Now think about this for a second, right? We could draw a little table to think about this, right? H, well, if 0 hours have gone by, there have been 0 doubles. After 8 hours, there's 1 double. After 16 hours, there's 2 doubles, etc., right? So what's an equation that relates the number of hours that have passed to how many times it's doubled? Think about that for a minute. Do you have it? It's actually pretty easy. The number of hours just equals 8 times the number of doubles. And that makes sense. If d is 1, if it's doubled once, then 8 times 1 gives me 8 hours. If d is 2, it's doubled twice, then 8 times 2 gives me 16 hours. Now notice it says solve for d in terms of h. That means that d must be h divided by 8. And again, check that with a couple of examples. If h had been 8, 8 divided by 8 would give us 1 doubling. If h was 16, 16 divided by 8 would give us 2 doubles. If h was 24, 24 divided by h would give us 3 doubles. 3 doubles in a day. All right? Now, it's combination of this equation with this equation that we're going to get to in letter C. In C, it says, using your answers from A and B, write a model for the population of fruit flies P as a function of the number of hours since there were 22 flies. Well, this is simple. We're actually going to use composition. We're going to compose this function with this one, or better yet, we're going to substitute. In other words, we're going to take this h divided by 8, and we're simply going to plug it in for d. And we can do that. Equals can be substituted for equals, so we can now say the population as a function of the number of hours is 22 times 2 to the h divided by 8. All right? And again, I would encourage you to test this, right? If h was equal to 8, right, then what would happen would be p of 8 would be 22 times 2 to the 8 divided by 8, but that would be 22 times 2 to the first, or 44, right, which is exactly what we want. We want, when we put h equals 8 into this function, for us to get 44 out. And if I put 16 into this function, I'd get 16 divided by 8, which would be 2. 2 squared would be 4. 4 times 22 would be 88. We would have quadrupled after 16 hours. But this is ultimately what we want to be able to do in the type of problems we're working on today. Now let's take a look at letter D. This is very, very important. By what percent is the fruit fly population, let me get rid of some of this stuff. By what percent is the fruit fly population increasing per hour? Show how you arrived at your answer. All right, now this is critically important. And you have everything you need to kind of figure this out right now, but it's a bit tricky. So what I'd like you to do is pause the video now and see if you can figure this out. All right. Well, it's very, very easy to see the percent that an exponential function is increasing and likewise decreasing if it's written in the form y equals a times b to the x. And we'll look at this a little bit more in a moment. If it's written like this, but right now this function doesn't look like this. I mean, sure, the a is 22 and the b is 2, but we don't just have an x up there. We have an h divided by 8. We need to just have the h up here, not the h divided by 8. So we're going to use a very simple exponent property to rewrite this. We're going to take advantage of the structure of this expression, and we're going to rewrite this as 2 to the 1/8 times h. Now you might say, well, that didn't do too much for me. Instead of having h divided by 8, I have 1/8 times h. Same thing. Of course it is. But now we're going to do one last little thing. We're going to rewrite this as 22 times 2 to the 1/8 all to the h. And you see now, this is my b. That's my base. So what I'd like you to do, if you haven't done this yet, is take your calculator and put in 2 to the 1/8 and see what you get. Be careful about it. All right, now 2 to the 1/8 is a messy, irrational answer. But if you take it out just a few decimal places, let me extend the page a little bit and bring this back up so you can see it. Ultimately speaking, and of course I can't do 2 to the 1/8 in my head, nobody can, but let me take a look. It's 1.0905, and I have my magic red dot there, maybe I'll make it black. Okay, now it's written in the right form. Now it's written like, whoops, a little equal sign might help. It looks like a times b to the x, except it's a times b to the h, but whatever. When it's written like this, we should be able to easily look at this and say, oh, it's increasing by 9.05% per hour. How do I know it's per hour? Because that's now the time unit of my variable when it's written like this. All right? I can't tell that it's increasing by 9.05% per hour when it's written like this. But as soon as I bring that 1/8 inside and I do the 2 to the 1/8, now I can determine what percent it's increasing per hour. Very important. All right? Take a moment. Let me kind of move off screen a little bit and bring this up some. All right, I think this is the most important piece down here. Take a minute and write down anything you need to. All right, let's take a look at the next slide and let's summarize it. The big idea, right? Exponential functions that we're used to are most often written like this, a times b to the x, right? Where a is the starting value. It's what you start with. 22 fruit flies, $500 in the savings account, 200 pounds of enriched uranium. I don't know why you'd have 200 pounds of enriched uranium, but of course we got radioactive decay coming. More importantly, the b, the multiplying factor, growth or decay factor, right? And again, if the variable up here is just x, or t, or h, or d, there's nothing modifying it. It's not x divided by 5, or 5 times x, or anything like that. Then we can look at the b, and we can figure out what percent this is growing for every unit of growth of that. So for instance, real simple exponential modeling kind of work, right? If we had bacteria that were starting with a population of 150 and we're growing at a rate of 7% per minute, we could all model this very quickly as the population as a function of minutes is 150 times 1.07 to the m. But let's say that we wanted this model in terms of hours instead of minutes. Well, it's very easy to form in terms of minutes. Then we could say, well, I know that the number of minutes is always equal to 60 times the number of hours. Then, of course, I could take that relationship and I could just substitute it into here, and I could get 150 times 1.07 to the 60h. And this would now give me my population model in terms of hours instead of in terms of minutes. Now, what it wouldn't do is it wouldn't immediately tell me by what percent the bacteria is growing per hour. To do that, I would have to do sort of what I did last time, group these together, multiply or do 1.07 to the 60, and then that would be able to tell me what percent this population is growing per hour. Okay? And we'll get more into that as we move on. So let's now get into a little bit of radioactive decay. Let's see how we do that in the next problem. All right, here we go. Exercise number 2. A radioactive material has a half-life of 35 years. And I think we've all seen radioactive decay problems enough to know that what that means is that every 35 years, right, half of the radioactive material is removed. We multiply by 0.5, okay? If a sub 0 represents the original amount of it present and t represents the number of years it has been decaying, which of the following models the amount a of the radioactive material still present after t years? It's a little multiple choice question, right? So think about this for a minute, all right? If we were doing this problem very similar to the last one, I might do something like this. I might say, well, the amount that's present, forget about putting a little parentheses there or anything like that, would be the amount that I start with times 1/2 to the h. Now, h doesn't mean hours right now. H is the number of half-lives, right? Now the real question is, how does h then relate to t, the number of years? Well, we could kind of pull a trick like we did last time, and we could say the number of years is equal to 35 times the number of half-lives. Remember, again, h is the number of half-lives. So if there's one half-life, 35 times 1 gives me 35 years that have passed. If 2 half-lives, right, if h is 2, then the number of years must be 70. Of course, what I really want is the number of half-lives solved for. So, just like before, I could divide both sides by 35 and say that the number of half-lives is t divided by 35. Now, I can take this and I can plug it up into my function and get the amount of radioactive material present as a function of the number of years is the original amount, which we don't know, times 1/2 to the t divided by 35, right? And that ends up being choice 2, right? Pretty easy. And again, think about it. If I said t was 35 years, and I put 35 up here, I'd get 35 divided by 35, which would be 1, and then I would get to multiply by the 1/2 once. If t was equal to 70, and I put 70 up here, I'd get 70 divided by 35, I'd get 2, and then 1/2 to the second would be 1/4, and then I'd only have 25% remaining. Remember, this 1/2 doesn't represent the percent being taken away or the portion being taken away. It actually represents the fraction of the material that remains radioactive. All right? Now let's take a look at exercise 3. If the correct model for exercise 2 was placed in this form, then what would be the value of b accurate to 4 decimal places? So if I want it in just y equals a times b to the x form, okay, instead of t divided by 35, right, what would be the value of b, and what does it tell us about the decay per year? Try to answer this question on your own. All right, well, we're going to pull a trick very similar to the one before. What we're going to do is we're going to take this expression and make use of this exponent property, which allows us to take this exponent and break it up so that we have 1/2 to the 1/35 all raised to the t. Now again, you need to be very careful on this when you put it into your calculator. All right, you could easily do 1/2 to the first and then divide the entire answer by 35. That would give you a completely wrong answer. But if we put that into our calculator and we want 4 decimal place accuracy, let me use my cheat sheet here for a minute, it's 0.9804. All right, so this is putting it into my a times b to the t form, right? Now, what's wonderful about that is once we have it in this form, let me make that decimal point a little bit larger, then we can really think about the decay per year. So what we're seeing is, forgetting about the 0.04, right? Just like pretend that's 0.98. What that means is every year we have 98% left of what we had the previous year, which means that about 2% of the material is decaying per year. About 2% is decaying per year. To be precise, it's more close to 1.96%, but it's good to make what I would call reasonable rounding arguments when they come up. You know, if somebody was actually asking us to do this and said, hey, you know, what percent is it decaying per year? Right, you could say, it's 1.96%, but even that's not exact because this 0.9804, I've only taken out to 4 decimal places. But saying, it's decaying about 2% per year, perfect. All right, let me step out of the way, take a look, and then we'll move on to the back side of the sheet. Okay, let's do it. Also move my cheat sheets a little bit. Let's take a look at exercise number 4. Now, again, keep in mind in all of these, right, we're kind of starting off simple, and then we're working our way up. But let's take a look at exercise 4. The number of people who know a rumor as a function of the days since it started is given by the function n of d equals 5 times 3.8 to the d. Write a model for the number of people who know the rumor as a function of the number of hours it has been spreading. At what percent to the nearest tenth is the rumor growing per hour? So now we've got an exponential model that shows us the number of people who know a rumor as a function of the days since the rumor started. All right? But we want it, instead of days, in terms of hours. And then we want to know what percent the rumor is spreading at per hour. Take a little bit of time and try to work this out for yourself. All right, let's go through it. So, you know, if d is the number of days, all right, and let's let h equal the number of hours, well, how do these two relate to each other? Well, the number of hours will always be 24 times the number of days. The number of hours will always be 24 times the number of days, right? It's like saying the number of days will always be 7 times the number of weeks, in which case we can easily solve this and say the number of days is equal to the number of hours divided by 24, and now we can figure out this function in terms of the number of hours. It's now going to be 5 times 3.8 to the h divided by 24. And this is a perfectly good way to leave that in terms of a model that gives us the number of people who know the rumor as a function of the hours that it's been spreading. But if we want to know the percent that the rumor is spreading per hour, now we've got to just have an h up here. We can't have an h divided by 24. But we play exactly the same game we did before, which is that we just manipulate this a little bit and we rewrite it as 3.8 to the 1/24th, all to the h. Again, the beautiful thing is we now have it as a times b to the h. All right, we just have to use our calculators to figure this out. We'll eventually take that graphing calculator out in just a little bit. Again, I have to do my own little cheat sheet because not even the smartest person on earth is going to be able to tell you what 3.8 to the 1/24th is. That would be a little bit silly. But it's 1.0572. Right? And now in this format, you should be able to look at that and go, oh, all right. The rumor is spreading, maybe I should say growing, but we're going to say is spreading at a rate of 5.72% per hour. Actually, it says to the nearest tenth, so just 5.7% per hour, right? 1.0572 indicates 5.72%, but they say just to the nearest tenth, so 5.7% per hour. Again, the only way we can really interpret these models and get that percent growth out of it is if it's written in that a times b to the variable. Not to the variable that's been modified, but a times b to the x, the h, the t, the whatever. And that's why we can say here it's 5.72%, whereas here or here, we don't really know. All right, write down anything you need to, and then we'll move on to the next exercise. All right, let's go through it. Exercise number 5, last one. Here we go. A slow leak of gas from a tank is causing the volume of the tank to decrease by 8% for every 10 minutes the gas leaks. The original volume of gas is 2,600 cubic inches. So let's make sure that we get it, right? The volume of the tank is going to decrease by 8% for every 10 minutes the gas leaks. All right, so after 10 minutes, decreases by 8%. After another 10 minutes, it decreases by 8% from what it was before. Again, it keeps going down. 8% every 10 minutes, and it's that 10 minutes that's tough. If they told me, it decreases by 8% every minute, it's a piece of cake. So let's take a look at exercise A. If m is the number of minutes, we're automatically going for it. M is the number of minutes the gas has been leaking, and V is the volume of gas left in the tank. Write a function for V in terms of m. Why don't you pause the video and take a shot at this right now? All right, I bet by now you can do it without kind of putting that intermediate step in. So let's do it. The volume as a function of the number of minutes is what we started at, 2,600. Now what would be that multiplying factor? Since it's going down by 8%, the multiplying factor would be 0.92, right? Not 1.08, that would be making the exponential go up. 0.92 makes it go down, but it's not 0.92 to the m, right? It's 0.92 to the m divided by 10, right? For every 10 minutes, we get to multiply by 0.92. So when m is 10, we get to multiply by 0.92 once. When m is 20, right? 20 divided by 10 would be 2. Then we'd get to multiply by 0.92 squared. Always loop back and make sure that you check if this is reasonable or not by just using numbers that you know are correct, right? M equals 10, m equals 20, m equals 30, etc. All right, let's take a look at letter B. Determine the number of minutes to the nearest minute that it takes for the volume of the gas to reach half its volume. Show your graph below, label all relevant information. All right, now this is where we definitely need our calculator. We needed it before to do, some of those ugly calculations like raising 2 to the 1/35th or 1/2 to the 1/35th. We definitely needed it for that. But here we're going to actually solve an equation graphically by using our graphing calculator. So let's bring it up. It's been a little while since we've done the Weiler snap. Here comes the calculator. All right, so we've got the graphing calculator, and now it's time for me to push some buttons. All right, now obviously what we're going to start with is just by hitting y equals and getting our function in there. So I need to put in 2600 times 0.92 raised to, and here of course I've got to use x, but I'll use x divided by 10. I can't use m in other words. Now I wanted to find out where that was going to hit half its volume, since we started off with a volume of 1300 or 2600, half of it would be 1300. Now to get a good graph, I really have to set a good window. And this window is going to be a little bit weird. Now I certainly don't want it to go from 0 to 365, but I'm not sure exactly what I do want it to go from. Maybe 0 to, I don't know, maybe it should just be an hour. Let's give it a shot and see what happens if we put 0 to 60. Remember, x represents the minutes. The x scale of 1 is fine. Oh, but the y, that's the volume itself. Now we could certainly put a minimum volume of 0 in, but the maximum volume, remember, we're starting off at 2600. So maybe what we'll do is we'll put in a volume of 3000. All right, let's take a look and see what it looks like. All right, our initial curve, that blue curve, is going to be the volume. All right, and then the second curve that comes on is now going to be that half volume. Oh, and they don't intersect. Now that doesn't bother me at all. It just means I have to go into my window and extend the time. I could maybe look at my table right now to get a sense, but let's just extend it out to 2 hours. Maybe that'll be enough for it to reach half of its volume. Let's take a look. Here's that volume of the gas decreasing in that classic exponential manner. Oh, there we go. Great. Now, of course, what I need to find is I need to find that intersection point right there. I'm on the TI-84 Plus, so what I'm going to do is I'm going to just simply go into my Calculate menu right above Trace, and I'm going to use the intersect. That's choice number 5. It asks me for my first curve, so I hit Enter. My second curve, I hit Enter, and then my guess. I'm just going to hit Enter again. All right, there it is. And my intersection is at roughly 83 minutes, 83.129504, and 1300. So let's do a little bit of sketching now, okay? I've got my graph up, right? I just need to do a good sketch. Remember, it's always good to sketch, to have your window on there. Boy, that just looked terrible. Let's delete that and try it again. Well, maybe just move those 2 dots out of the way. Let's try that. This just doesn't like me now. Anyway, that's supposed to say 3000. Apparently it's not going to work out very well. Maybe it's because I have this thing there. 3000, doesn't really look like it, but that'll be fine. And my time, 120 minutes. Now my exponential curve, right, looked something like this, and I should label it with its equation. Wow, this thing is just having fun right now. How about y equals 2600 times 0.92 to the x divided by 10. Maybe I'll just now drag this in here. Please ignore all those things that kind of look like smiley faces and dots and whatnot. Oh, not the entire curve. The entire curve, I lost it. All right, now let's draw on my y equals 1300. And I need that great intersection point, which was at about 83.1, oh, technology, and 1300. Of course it's at 1300. All right, so the important number, the one that's supposed to be sitting right in here, is 83.1. And what do we want? To the nearest minute. So to the nearest minute, it takes us 83 minutes. Wow, that was amazingly annoying. This graph should look a lot better. It should look like an 83. It doesn't. That should look like a 3000. It doesn't. Smart boards. Anyway, can't live with them, can't live without them. I think that we can probably put the calculator away now. Bye-bye. All right, excellent. And now let's take a look at the last part of this problem. Similar to before, by what percent to the nearest percent does the volume of the gas decrease in 1 hour? Show how you found your answer. Show how you determined your answer. By what percent does the volume decrease in 1 hour? All right, pause the video now and take a little time to think about this. All right. Now this is a little bit tricky because before we would oftentimes take our equation, actually let me just write it right down here. We would take our equation like this, y equals 2600 times 0.92. Let me do this with the m divided by 10, and we'd say, all right, great, there it is. You know what I mean? And then I'd maybe bring that 1/10 in. The thing is, what that would do is that would tell me the percent that it was decreasing per minute. If I really wanted to know the percent it's decreasing per hour, then what I'd really like up here is I'd like to have this in terms of h for hours. Now, how do h and m relate? Well, we know for certain, actually let me get rid of that the number of minutes will always be 60 times the number of hours, right? Now, I don't need to solve this for h. I can actually take this and directly substitute it in here. So let's get this model in terms of hours instead of minutes. All right, 0.92 to the 60h divided by 10. All right, can't lose that divided by 10, right? Just because I put the 60h in for the minutes. Now, of course, 60 divided by 10, I can rewrite that as 0.92 to the 6h, right? 60 divided by 10 is just 6. But remember, this still doesn't help me in terms of the percent that it's decreasing per hour. What I really now need to do is write this as 2600 times 0.92 to the 6th to the h. And this is what I need to have my calculator for. So, if you haven't done it yet, do 0.92 to the 6th and see what you get. All right, it's still a little tricky, by the way. It's not so bad when it's increasing, but when it's decreasing, students find this quite a challenge. Oh, there we go. Apparently I find it quite a challenge just to go from one board to another. Anyway, so assuming that we've done that 0.92 to the 6th on our calculator, my cheat sheet says it's 0.6064, accurate to 4 decimal places. Now, what's tricky is you don't want to look at this and say, oh, it's decreasing by 60.64% for every hour. The 60.64 is what remains after each hour, not the percent that it's decreasing. In other words, to figure out really the answer to this question, we want to do 1 minus 0.6064, which is 0.3936, and therefore it's decreasing by 39% per hour, right? It's decreasing by 8% every 10 minutes, but it's decreasing by 39% for every hour. All right, let me step back, have you take a look at this, and then we'll wrap up the lesson. All right, let's do it. So most students at this point are very, very comfortable with modeling exponential functions where you've simply got y equals a times b to the x. And you're given some percent increase for every 1 unit of increase in x. Now, x might represent the number of hours, the number of minutes, the number of days, etc. But what happens when they tell you that it increases by a certain percent or decreases by a certain percent for an interval of time that isn't 1 unit, 1 hour, 1 minute, 1 day, 1 second? What if it's 10 minutes? What if it's 5 minutes? What if it doubles every 4 hours, right? How do you deal with that? And that's what we worked on today in our lesson. We oftentimes took advantage of very simple relationships between the number of hours and the number of days, right? The number of minutes and the number of hours, right? We did all of that, and then we used the structure of expressions along with properties of exponents to be able to manipulate these exponential models to answer questions we needed them to do. All right. Again, you'll get more work on exponential modeling as you move on with the course, but for now, I just want to thank you for joining me for another Common Core Algebra 2 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.